Okay, welcome. This is the video for Worksheet 2. Hopefully your semester is going along really well so far. And don't forget, if I am talking too fast or too slow, you can adjust the playback speed. One of the benefits of having remote learning. Okay, so we have a couple things we need to talk about before you can start on your work. Apparently, I need to talk to my computer for a second. Hopefully I have a mutual understanding with this device at the moment. Okay, so the first thing you're going to encounter in the worksheet is a question that says initial value. And for initial value, this is very easy. So f of whatever it is equal to whatever it is. The initial value simply means what is f at 0. So in more complex questions, it could be a little different, but there's nothing in this class that's going to violate that. We're going to start, t is usually the function when we're talking about time, and then initial refers to the first time. So when you're thinking about time on a continuous scale, you start the clock at 0 and you run the clock forward. So the initial value is 0, as opposed to the initial thing is not 1, it's 0. So you start the clock at midnight and you start running the clock. That's all that means. So throw t equals 0 into that equation and get the answer. Okay. The next kind of question you're going to get is growth rate, and I want to pause for a second and explain, because that's the way it's worded in the worksheet is ambiguous on purpose. What is meant by growth rate? There's two common answers that you can give, and they're both correct, but it depends on the context. It could be the linear growth rate or the exponential growth rate. Here's some examples. If I say how fast the temperature is increasing in degrees per hour, this would be an example of a linear growth rate, okay? But what if I'm talking about my bank account and I say, well, I'm getting an interest rate of 10% yearly. What does that mean? Well, that means by implication that it's a multiplicative growth rate. When you're talking about a factor or a percent, you say this, and this is a problem in English. This is an English problem, this is a math problem. English problem. Math has no problem understanding what's going on. It's because we as humans use the same language to describe two different things which are quite different, but they're similar in some way. And so therefore, since we have two definitions that are very, very similar, we confuse students all the time. In the context of this problem that you're given on this worksheet, we have, let me give you a similar problem. It may say P of t equals 17, and then maybe this is 14 over 3 to the power of t, for example. In this case, this guy is your initial value, because if t is 0, this whole thing is 1 and that wipes out. So this is your initial value, and this guy is going to be your growth rate. And so you have to consider the context, and sometimes exercises are written on purpose to be ambiguous, but in this case, you have this expression written right out in front of you in that format, and so it's clear what is meant by the question. It is in the context of which other exercises are near it, and so on and so forth. But if you are ever confused, you need to ask. If confused, ask. Ask, ask, ask. No problem in asking, especially when the question is growth rate questions. Just as a cute little aside cameo, this COVID stuff. Okay, so you can talk about two different kinds of growth rates. You usually see the linear charts, and in this case we're talking about, from one day to another day. If this is the totals, you want to know what the new case rate per day is. What is the new case rate? That means, like, if you're just looking at the linear graph, you're asking about a linear increase. But if you're asking about the exponential curves, and right as I'm writing this, sadly, what's happened to the exponential curves is they seem to slow down, but then they're just going off to a different slope. It's really sad. But anyway, in that case, if you're doing this kind of questioning, you may say, what is the rate, what is the percent change in a month or a week? What is the percent change? And that is essentially asking the other kind of growth question, more like your bank account. What's the percent change? What is the growth rate in terms of when we're talking about R? The R value you hear about in the news or R naught. It's talking about how transmittable this virus is, and it's actually getting down to this idea of what's the exponential growth rate of the disease over a certain amount of time. Or instead of using time as the standard, it's how many people transmit to how many other people. But it's a very same concept, very similar concept. Okay, so here we have a question of how do we create exponential functions given 2 points? All right, if we have 2 points given, if you recall, we talked in the last video about how you create a line out of 2 points. And this is an analogous question, but now it's for the exponential world. How do you create an exponential growth or decay curve from 2 points? And this is going to be your initial their initial time, and this is going to be your initial value. And so what you're going to do is you're going to put the initial value here, and you're going to reset the time clock. So A is your initial time. So you're just going to shift everything so that you can start at any time you want. And then this denominator here in this exponent, I like to call this is my own name for it, the natural time step. What I mean by natural is because of the way your data were handed to you. And then this piece here is going to be your exponential growth rate. And in some of your questions, you may want to figure that out. So what do you do once you have assembled your answers? So for example, this is really easy to pop something in here. Let's see, if I have 3, 7, and 4, 9, what do I do? Well, I'm just going to say y equals 7, 9 over 7 to the power of t minus 3, but 4 minus 3 is just 1. So I can say divide by 1, but that's kind of pathetic, so I can just leave that out. Okay? So what if I wanted to convert this into something else? Maybe I don't like that format. So what I can do is multiplying, you add exponents, right? So you have like 3 to the 7 is 3 to the 4 times 3 cubed. You just add those exponents. So you can undo that same thing. You can just unstack these guys, and you put this all in your calculator, and you simply type in what is going to be your initial value, because now you're recentering at t equals 0, so your initial value is going to be 7 times whatever quantity 9 over 7 is raised to the power of minus 3. So how you're going to key that in is 7 times, open parentheses, 9 divided by 7, close parentheses, to the power of, open parentheses, minus 3, close parentheses, then hit equals, and then you're going to end up with the expression that you want for your initial value. And then of course your growth rate, you're going to key that in very easily, 9 divided by 7 equals, and you're going to copy down those numbers. Okay, so you're going to use those kind of calculations to figure out things on the worksheet. But I haven't answered the question yet. What happens if you ended up with something that looks kind of like this? You have, don't worry about your growth rate, you're fine with that, and you ask me, well, what happens if there is a division in my exponent? Well, that's no sweat. Okay, so you just go like this. You say find 3 to the 1/2 square to the t. That's how you decouple this piece, because when you have an exponent to an exponent, you just multiply them together. So if you want to uncouple them, you just stick the t outside, and whatever else remains, you just stick it right on your base, and then away you go, and that's not a problem. And so then whatever that is, you calculate this in your calculator. It's just square root, but let's say you didn't know that. 3 to the power of 1 divided by 2 equals. Some people on your calculator, if you have a calculator, this is going to look like a button that says y to the x. It's the same button. It just depends on the style of the manufacturer, what your button looks like. You can also be lazy like me and just type it into Google. I can literally just say, okay, Google, or let's see, I guess I'm processing a video. Okay, so I can just say 3 to the power of 1 over 2, and Google will give me that answer, and then it gives me like this little push button thing. So if you don't have a calculator on the ready, Google will always fill in for you. Okay, so that covers that bit. Of course, what if you say to me, okay, that's okay when they're separated, but I get really confused. What if they're all together? So you know what? I'm just going to do a generic example to show you where everything ends up if you have any combination of these things going on in your problem. So the first thing you want to do is say, well, you can split it differently if you want, but here's the way I prefer to do it. I can just split up those fractions, and then I can do the following. I can say b to the 1 over d to the x, and then this is b to the minus c over d. And so if you want to know what your initial value then becomes, it's all this gobbledygook. You multiply it together, and your growth rate is this mess. Okay, so it's really not that big of a deal. It's just annoying, and that's just a calculation you need to be able to handle. I used to go out to Chinese restaurants back before COVID, and they would give you chopsticks in a little bag, and then inside the package it would say, you take them out and the package says, now you can pick up anything. I just always love that phrase. Like, okay, all it takes is one quick little discussion and then you're an expert. It's like, yeah, right. And I often do that to my students. It's like, oh, let me just show you this. Now you can do any of these exercises. Well, technically that's true, but we still need some practice. So here's a question. What if we want to do PERT-PAT conversions? I like to call them PERT-PAT because that's the way I think of it. But in the worksheet, this is actually called P naught e to the kt. But I like to call it PERT or PECT or whatever you want to call it. But I call it the PERT-PAT problems. So first of all, if you want to convert between any two formats for an exponential function, and PERT to PAT is just one of the many ways you can convert, all you have to do is line up the various pieces and figure out what's going on. So if you have a problem that's like 7 times 4 to the t, and you want to convert it into this other version, the PERT version, then what you're going to do is say, okay, p e to the rt is what? And it's like, well, actually the nice thing is p. So just get rid of the p's. Okay? They're not actually helping anything. What did I say? I think it was 7. And you know what? The t's, you can get rid of them too. And so if you want to find r, you just say natural log of 7 is equal to the natural log of e to the r, which is r. Because you can pull the exponent out, and the natural log of e is 1. So don't forget, natural log of e actually is 1 log base 10. Anything log base itself is still going to be 1. And the natural log of 1 is 0, but actually any log base 1 is 0. So those are things you need to have on the ready. Going the other way is even easier because you don't have to do any solving. If you have a question where you have a PERT and you want a PAT, you literally just take e to the r. So if I have like 14e to the 7t and I want to convert it, it's just going to be 14e to the 7t, and you just type that into your calculator, and whatever that number is, that's the a. E to the 7 is just a. It's just you have to get out the natural log to go back the reverse direction. Okay, but it's still not that bad. Okay, what other things might you be expected to demonstrate? Oh yes, the simple log reviews. Okay, so log, regular or natural log, it doesn't matter. Natural log of a times b is natural log of a plus natural log of b, and natural log of a divided by b, that turns into a subtraction. And you want to know that if you have some expression natural log of x to some power, you can just drag that power right outside. In fact, the whole fact that we can do this is why we take the natural log. So when you have something like 7 to the x and you're like, oh shoot, I need to get at that x, and there's maybe a 14 on the other side, you can just take the natural log of both sides, and then you can go, aha, x natural log of 7 is natural log of 14, for example. And then that x is now in a nice position. So what logs do is logs turn exponential problems into lines. And that's the core reason why your author wants to have you review the formula for a line at the same time as the formula for an exponent, to try to get this idea into your head that when you're doing logs, in some sense, it is kind of like working with lines, but it's in a multiplicative sense as opposed to in an additive sense. Try to rewire your brain a little bit to realize that that kind of works. Try to stretch the way you think a little bit. So, for example, x squared times x to the 4th equals x to the 6th. That makes sense, right? Because as x squared, x to the 4th is equal to x to the 6th. So if you can understand this, then this whole thing should make sense. So natural log of x squared times x to the 4th should equal natural log of x to the 6th. Natural log of x squared plus natural log of x to the 4th should equal natural log of x to the 6th. And that makes sense because y, I'm going to just move some of this, I guess I'm going to move some of that stuff up. I don't know, I'm just going to erase it for a sec. I don't need that anymore. Here we go. Alright, so this is 2 natural log of x plus 4 natural log of x equals 6 natural log of x. And this works because when you have an exponent, it's allowed to pop down. All those exponents pop down. And so hopefully that's brushing out the cobwebs out of your head. Now, we have exponential functions and we have log functions, and they are inverses of each other. So, you know, most of the time, like if we have a line and its inverse is a line, they both look kind of the same to us, but a log and an exponent are written very differently, even though they're based on the same concept. So you have to pause a second to figure out what's going on, but all the exponential graphs, they either cross the y equals x line or they don't. It doesn't matter really. But they have to cross the line right here at 1. Initial value, well, it's whatever it's scaled by. Okay? So if I want to say something like y is equal to 7 to the x, I get 0, 1. I very, very frequently cross 0, 1 with my exponential graph. And again, if I wanted to change that, I wouldn't change the base. I'd have to change the multiplier, in which case then I would cross the axis here at 0, 2. Okay, so you can't change where it crosses the axis by changing the base, like where the 7 is. That 7 doesn't matter. Right now it's only seeing the 2. Alright? How do I find the inverse function of that? Well, if it crosses the axis, it's going to cross the axis, I'm sorry, if it crosses the y equals x line, if the original function crosses the y equals x line, then the inverse function will also cross it the same number of times, and it's going to have the same structure. So the log graph is going to look the same as the other one. It's just going to be flipped. Okay, so what in fact is the expression which we would use? How can we solve this? Well, let's do what we did in the last video. We just flip x and y and see what happens, see what kind of a mess we get into. So x minus 2 is equal to 7 to the x, up 7 to the y, and I want to solve for y, and I say, oh gee, I don't know, natural log of x over 2 is equal to natural log of 7 to the y, and so I get natural log of x over 2 is equal to y natural log of 7. So y here, which is f inverse, y equals natural log of x over 2 divided by natural log of 7. Which brings us to another important point. This is actually equivalent to saying y is equal to log base 7 of x over 2. Those are two equivalent ways of saying the same thing. I like to call this the love the one you're with rule. There's a song that says, if you can't be with the one you love, love the one you're with. It's horrible advice for love, but it's great advice when you're dealing with logarithms. You can take the log of anything you want. It could be the log of 47, who cares? Log base 47 of x over log base 47 of, like, b. Whatever base system happens to be lying around, it's usually natural log, then you just use it to take the log of whatever you wanted to take the log of, and then to convert, you just take the log of the base you wanted. Okay, so if you have log 10 tables floating around, you just use them, and then you just take the log you need and then divide by the log of the base you really wanted. Okay, so that's a fun trick. You need to know that when we use the word log, this is very, very ambiguous. It could mean natural log, it could be log base 2, it could be log base 10, it could be log anything you want based on the context of the research you're reading about, or the context of the authors. So don't ever make an assumption about what log means. Always ask or read the paper you're in. It's very easy to assume they mean base 10 or assume they mean e, but it's not always true. So if you want to be very explicit about which log you're using, ln always means natural log. I've even seen it as lg. Okay, so I like to use natural log for a lot of reasons, and one is that it's not ambiguous. And sometimes it just means any log you like, as long as you are consistent, then it's fine. Because one log is just any log, and as you can see, logs are all the same. They're just off by a scalar multiple of each other. So log is log, but when it matters which base it is, then go ahead and dig a little bit deeper to figure out which log you're looking at. Okay, now, half-life. We got to talk about half-life. There we go. I guess it's our last topic for this video. You can use half as your growth rate, and then everything I'm going to tell you is not new. It's just based on these other things I just told you. I just realized I have a typo. Hold on a second. Did you even notice the typo? Some of you probably did, and it probably drove you nuts. Okay, so let's say we find, I'm going to just give you an example and then I'll talk about it a little bit more. So let me type down the problem. Okay, so we're going to ignore all the realities of mathematics and carbon-14 dating and just look at the pure exponential decay problem. Anytime you're in a math class, you can pretty much assume that it's a pure math problem, even though it's couched as a real-world problem. And that's actually true very, very often in a math class. But in this case, we're just going to say an object is found during an archaeological dig. The person who found it thinks it's about 2,000 years old. Carbon-14 dating shows that this object has 99% of its original carbon-14. Using an estimate of a 6,000-year half-life for carbon-14, estimate the actual age of the finding. So in your worksheet, you're going to have different numbers and a different, like a more accurate estimate for the half-life. Just wanted to show you the process on this. Okay, so what you're going to do is you're going to say, well, this is just an exponential problem. Y equals P times 1/2 T. It's just the A in the PAT formula. And it's going to be T over 6,000. Okay, and so P in this case is just 1, so you don't have to write it at all. So the 1 is essentially silent. Okay, so you know that you start at T equals 0 with 100% of your carbon-14, and if T is in years, you want to know how many years old it is. Then what you do is you say, okay, fine, it currently has 0.999, but we want to find the T value that makes this work out. And so what you do is you take the natural log of both sides, and of course that exponent pops down, T over 6,000, times natural log of 0.5, and then you solve for t, natural log of 0.99 over natural log of 0.5, and then that 6,000 ends up on the other side with the natural log of 0.99, and you get natural log of 0.5 under here, and t goes over there. So I'm not going to answer this question, I just wanted to show you the process. Then you find the time at which, like, this is the age of the object. Okay, so this is the carbon-14 age of the object, and then what you do is you say, well, compare that to the person's claim, and we're not going to do any statistics here. We're literally just going to say you're crazy or it's plausible. Okay, and notice that if you essentially confirm the date, it doesn't mean the object is authentic, it just means it's old. It also could have been made with an old material, so it is kind of tricky. There's a lot of tricky realities, but as far as we're concerned, for the purpose of the math problem, you're going to basically say this thing is old or it's not. Now in your exercise, I'll let you play with it, but you do have to sort of consider if there's a date range like from here to here where the thing could be, and you're just outside the edge of it, maybe it's okay. The carbon-14 dating is meant for things that are extremely old, and it is not that perfect. Okay, so you have to kind of keep that into consideration. Just sort of try to balance your pure math side with the realistic side. That's, I guess, the best bet, best advice. Okay, so I guess that's all I need to tell you for this worksheet, and I look forward to seeing you in class.